Okay, so we have now developed the formula for the surface area of some curve y equals f of x, rotated around it. Does it really matter if we use, okay, rotated around the line y equals c, although you know we could just subtract c from the function and get a new function that was a little bit closer to the axis. Horizontal, vertical axes are not going to work so well in this. But from A to B, we're talking about, is that how it works? That far in, something like this. We're talking about the surface area of something like this. And the formula was the area is 2 pi the integral from A to B f of x minus c times the square root of 1 plus f prime of x squared dx. Now you would think that most of the time you wouldn't get something that was nice to integrate, and you would think absolutely correctly. For example, oh man, can we even do straight lines? I think we can do straight lines, but it's ugly. Let's do a parabola. 1, 2, 3, 4. Standard parabola. Let's just integrate y. Find the surface area of y equals x squared, rotated around just the x-axis. So what is this surface area? How bad could that be? Well, following the formula, the area is the integral, what are we doing, from 1 to 2? So 2 pi integral from 0 to 2 of x squared minus 0, because we're just using the x-axis, the square root of 1 plus the derivative of f, which is 2x squared, so that becomes, which is 2x. The derivative of x squared is 2x, the square of that is 4x squared dx. And that's not pleasant. I think later on this semester we will be able to deal with things like this. For the time being, the only trick we really have is to set u equal to 1 plus 4x squared, and du would be 8x. But we have x squared, it's not going to work out. So let's do one that does work out. Let's find the surface area of a sphere of radius r. Wouldn't that be lovely to know the formula for that? Well, what we do is, to get a sphere of radius r, we rotate the upper half of a circle around the x-axis. Now that would be x squared plus y squared is r squared. It goes from negative r to r. And when we rotate this around the x-axis, we get the sphere of our dreams. The upper half curve is just y is the square root of r squared minus x squared. Its derivative dy dx is 1/2 r squared minus x squared to the negative 1/2 power times the derivative of what's inside, which is negative 2x. The 2 cancels with the 1/2, and let's see, this is negative x over the square root of r squared minus x squared. Aha! Now our formula, to remind you, we take that derivative, we square it, add 1, put it in the square root, put an f of x out front. So our area is going to be the integral, put the 2 pi out front, from negative r to r of the function, which is square root of r squared minus x squared, times the square root of 1 plus that derivative squared. Now this thing squared, that's kind of nice. That's x squared over r squared minus x squared. The negative goes away and the square root goes away. dx. And what's even lovelier, and I'm going to skip a step for the sake of space, I'm going to turn this 1 into r squared minus x squared over r squared minus x squared in the interest of getting a common denominator. And when I add that to x squared over r squared minus x squared, I'm just going to get r squared. The x squareds will cancel out. So what we will have is 2 pi integral from negative r to r square root of r squared minus x squared of just r squared over r squared minus x squared. And if I split that up, it's the square root of r squared over the square root of r squared minus x squared, which has the even more amazing and beautiful property of those things going away. The square root of r squared is r, and that's even a constant. This is just 2 pi r integral from negative r to r of nothing with respect to x, which is, well, nothing. 1, the multiplicative nothing. So this is 2 pi r. You guys wait outside for a sec. I just have x, whose derivative is 1, from minus r to r. That will be 2 pi r times r minus negative r, also known as 2r. 2 pi r times 2r is 4 pi r squared, and this is in fact the surface area of a sphere of radius r. But really, the whole name of the game is knowing this formula. Knowing this formula, knowing how to apply it. You take the hardest thing is, 2 pi, easy, knowing where it begins and ends. If they don't tell you where it begins and ends, you pretty much don't know anything. Your function, copied straight out, square root of 1 plus the derivative of the function squared, which is why the first thing you sort of do is you take your function, you take your function, and you take its derivative, 2x, and you square that, 4x squared. Or you take your function, square root of r squared minus x squared, you take its derivative, you square it, and this is just amazing that this one comes out. What else can I do? More examples? I don't know. I need to work on getting you better at plugging in formulas, so we'll see what happens.